Honors Pre-Calculus students, welcome to your 12.1 notes. This is the beginning of the end for this course. It's one of the best chapters though. We're going to start talking about limits. You might also think of this chapter as being chapter 1 from your calculus book. Well, let's get started and see what this is about. So the intro to limits is where we begin. The concept of the limit is fundamental to the study of calculus. It's really the big thing that they look at in there, or that you will look at in there when you make it. So we're going to start with number 1 here. It says find the maximum area for a rectangle that has a perimeter of 28. So what I'm going to do is go ahead and mark one of the side lengths. I'll just use the width as my side, is x. If the perimeter is 28, then these two sides have to sum to 14, so I'll make this side right there, the length, be 14 minus x. Now what I want to do is take a look at how the area would change based on the value for x. So I'm just going to pick some values. I'm going to compare x to the area, and we're going to see where we can maximize that area. So I'm going to just start with x being 1. So this would be a 1 by 13 rectangle. If x were 2, this would be 2 by 12, so we'd have an area of 24. If x were 3, this is 3 by 11. And you guys can see the pattern here. If it's 4, we're up to 4 times 10, which is 40. You'll notice that the area keeps increasing, but the change is not in a linear pattern. Some of you may recognize this pattern. If you do, that's great. If you don't, stick with me. With 6, we'd have 6 times 8, which is 48. At 7, the length and width are the same. That area would be 49. If we kept going, if x were 8, you'd have 8 times 6, that's 48. This pattern would repeat all the way down. Now there's no reason we have to stay with integer values, but in this case we can clearly see that when we get to the point where we have length and width that are the same, in other words a square, we have our maximum area, which would be 49 square units. Alright, so the definition of a limit is connected to this in some ways, but if f of x becomes arbitrarily close to a unique number L as x approaches c from either side, that means from both the left and the right, then the limit of the function as x approaches c is L, or your limit. So we're going to put that concept into practice here. We want to use a table to find the limit of the given functions. So what I'm going to do is this. By finding a table, I know I need to get values in the case of number 2 that are close to 3, but we need to approach from both the left and the right. I'm going to use these values. There's nothing magical about them, but I'm going to go 2.5, 2.9, 2.99, and 3.01, 3.1, and then we'll go 3.5. Again, no magic, just simply numbers that are getting closer and closer to 3 without actually being 3. Now I'm just going to approximate these numbers. We've got 2.41, and yes, I'm using a calculator for this. It might not surprise you, but I'm actually using Desmos to make this happen. At 3.01, we'd also be at 2.50. At 3.1 would be at 2.52. Let's try that again. And then finally at 3.5 would be at about 2.59. Now really what we're looking for here it's not any of the values that we see there. It's basically predicting what would be in between those two. And I think it's a pretty obvious one here. In between 2.99 and 3.0 is where x is 3, and our limit, of course, would be 2.5. Now, in some of these problems, you can actually just plug in values, and as a matter of fact, number 2 would have been a case like that, but you can't always do that. Let's look at number 3, and I'll show you why. If we were to try to plug in 5, we would have division by 0. So in this case, we cannot actually plug in 5. We have to use the same method though, and we trust it. Now again, we're looking to see if the graph approaches the same point from both the left and the right. So I want to get close to 5. I'm going to use numbers like this. This time I'll go 4.8, 4.9. We'll do that 4.99 thing again. Then 5.01, 5.1, and then how about 5.2 to finish it off. Again, nothing magical about these 6 numbers, just the ones that are close to 5, both on the left and right. So let's see what happens. Now, actually, this is kind of an interesting one because our x minus 5s, if you factor the numerator, we'd have x minus 5s cancel. So basically, if you graph this on your calculator, it's going to look like a line. But there is a hole in the graph at 5. So anyway, because of that, it's pretty easy to find the y values. We would just have x minus 2. So this would be 2.9, 2.99, 3.01, 3.1, and then 3.2. And again, as we saw in the last one, what we're doing is we're trying to predict what would be in between those two. And again, I think it's pretty clear that at 5, our value would be 3. Now this is where limits are a little different than just simple evaluation, because the limit does exist, even though in this case the actual value of the function f of 5 would be undefined. Alright, continuing on. Now we're going to consider this scenario of a piecewise function, like you see here on number 4. And we're trying to find the limit as x approaches 8 for the given function f of x, and you can see the function f right there. But you'll notice that this function has the pesky stipulation that when x is equal to 8, the graph just has this one random point out there. Everywhere else it follows this pattern for x minus 7. Well, let's go ahead and do this the same way we've done the last couple, where we create a little chart to compare our values. So I'm going to use x, and I'll just go with f of x since that's what they're calling it here. We could use y, that would be fine. But again, we're trying to approach 8. So I'm going to use maybe 7, 7.5, 7.9, and then I'll repeat that pattern on the other side of 8, 8.1, 8.5, and finally 9. And then our job is, at this point, to plug in these values. Now you'll notice that the values I've chosen, the first rule, 4 times x minus 7, applies to all of them. So this would be 23. Let's see, 28 plus 3.6, 24.6 if my math is good. That's always questionable. 25.4. That seems good. This would be 27. And then finally 29. Really should have used the calculator on those. Wouldn't surprise me if I made a silly mistake. But I think I've accomplished my goal. I can kind of see what's going on here. If I look at 7.9 to 8.1, and you can see there's definitely like a linear pattern going on here. So again, I'm trying to read between the lines right here. Now another way I would think about it was, well, what if I just plugged in 8 right here to this first rule? 4 times 8 is 32, minus 7 is 25. Now, that is, in fact, the limit as x approaches 8 for that function. Now, as you know, if we actually asked you to evaluate f of 8, your answer would be 12. That's a different answer. The limit means the graph is approaching that point from both sides, so even though it kind of jumps down to 12 momentarily, the limit is not affected. All right, so let's take a look. Just a couple of quick questions here on number 5. It's just showing you that some of the mathematical principles we're used to with functions can still be applied even when we're talking about the limits of those functions. So if you know the limit as x approaches c of f of x is 5, and the limit as x approaches c of g of x is negative 2, and then you're asked to find the limit of 2 times f of x, that would just simply be 2 times 5, or 10. And the limit of as x approaches c of f of x divided by g of x would be 5 over negative 2. So you could call it negative 5 halves. You could call it negative 2.5. It's kind of up to you. And then finally, the limit as x approaches c of the square root of 5 times f of x. That would be 5 times 5. So that's 5 plus 2 times g of x. So that's negative 4. So the limit as x approaches c of that is 1. All right, so we've looked at some examples of limits that do exist, but those of you that have watched Mean Girls know that there are times when the limit does not exist. And so we're going to look at the three cases where that would happen, where the limit does not exist. So the first one on that is when left and right behaviors are different. So in other words, the graph approaches a different place on the left than it does the right. You can see the graph here is x equals 3. We'd be right here, and from the left, this graph approaches 6. From the right, it approaches 5. They're not going the same place. Therefore, we have no limit at f of x as x approaches 3. So the limit does not exist there. Another possibility for limit not existing is when we have unbounded behavior. So on number 2, the example you see here, even though technically these graphs are, I guess you could try to argue, we're both headed to the same, they're headed to the same place on the left and right. It seems kind of weird to say what's the limit and then say it's infinity. That kind of is oxymoronish. All right, and then finally, and this is my favorite one, but it's also the weirdest one, is, I don't know, that's surprising, but is oscillating behavior. And this is a really strange graph, sine of 1 over x. You can see it here. It looks fairly harmless. It's just, the curve, and it kind of bounces back a few times here and there in the middle. But if you look at that graph more closely, it's this part in the middle that's really crazy. I've actually got it graphed here for you. I'm going to show you. Looks pretty harmless there. But watch what happens as I stretch this graph out, and look how many times this thing bounces back and forth. It gets harder and harder to stretch this because I have a hard time not grabbing the graph because it's getting closer together. But this is like infinite. That mess in the middle. It doesn't matter how far I zoom in, how many times I stretch this graph out. It's going to be an infinite number of times here in the middle. That's why it just looks like a big red blob right there. That's what it should be because it's infinitely oscillating back and forth. It's impossible to determine what it is approaching, and therefore the limit does not exist. All right, now on more simple problems, when limits do exist, we can actually use direct substitution to find limits. I think you'll like these problems, and they move very quickly. You'll see why. So we're going to use substitution here. The limit as x approaches 3 of x cubed means that we just simply substitute in a 3 for x, and we have our limit. And yes, folks, that's all there is to it. So I think you could probably handle all of these. 4 times negative 2 gives us negative 8. Little trig going on here. The cosine of pi, that would be negative 1 divided by 3 pi. The limit as x approaches 25 of 2x plus square root of x, that would be 50 plus 5, or just simply 55. Now these are not that challenging. You do have to think a little from time to time, like, oh crud, we got a cotangent. All right, you'll survive. So here we go. The limit as x approaches pi over 2 of the cotangent of x times the sine of x. Now remember, the cotangent is, pi over 2 is at the top of the unit circle, so our ordered pair there is 0, 1. So your cotangent would be 0, and your sine function there would be 1. So you have 0 times 1, or just simply 0. And I'm going to do these last couple fairly quickly. When we plug in 3 there, we'll square it, and we'll just get 1. Here, when we plug in negative 2, it's 4 minus 14. That would be negative 10 plus 12 would give us 2. And if you notice, h and g, the numerator on h is already covered on g, so I can use, it's basically just 2 over negative 2 plus 4, so 2 over 2, which would just be equal to 1. All right, folks, I hope that this lesson made some sense to you. I know it's really not the most difficult one we've ever seen, but it's a good start to our study of limits. Have a spectacular day.